Hello and welcome to the Maths 2 component of the online BSc course on data science. Today's video is a continuation of the determinants topic that we have been studying. So, this is part 3 of that same topic. So, let us recall quickly what we did in the previous so far in this topic. So, we have defined for a 1 by 1 matrix that the determinant of the matrix A is just the number A. And then we have seen that for an n by n matrix, the determinant is defined inductively. So, we did the definition explicitly for 2 by 2 and 3 by 3, and then I showed for 4 by 4 how I can use a 3 by 3 definition. And then we said that in general we use the minors or cofactors corresponding to the first row in order to define the determinant. So, that means the idea is if you know how to define the determinant for n minus 1 by n minus 1 matrix, then you can use this procedure to get it for the n by n matrix. Okay. So, just to recall, the ijth minor is the determinant of the submatrix formed by deleting the ith row and jth column. So, you have n rows and n columns, you delete the ith row and the jth column, and then you are left with an n minus 1 by n minus 1 matrix, and then you take the determinant of that. Okay. And the ijth cofactor is minus 1 to the power I plus j times the ijth minor. Okay. And just to recall again, this was the final thing that we did in the previous video. We have seen that the determinant of A is minus 1 to the power 1 plus j A1j M1j. So, this was given by what I called expansion along the first row. Okay. And then you can take this minus 1 to the power 1 plus j inside along with M1j, and then you can replace it by C1j. Yeah, that is why we define the cofactor, so that we can get rid of the signs coming here. Okay. So, this is what we have studied so far. So, why did we study the ijth minor or the ijth cofactor? Because it is not occurred so far. So, that is one of the things we will see in this video, and we will also see some other properties of the determinant. So, why did we define the ijth minor or the ijth cofactor? So, the reason is because we had a formula for the determinant, in fact the definition, in terms of expanding for any row or with respect to the first row. And now what we are going to see is that you can actually do this with any row or any column, and there is nothing very special about the first row. Okay. So, this is called expansion along any row or column. Okay. So, here is what happens when we do expansion along the ith row. So, in that case we can write the expression for the determinant as the sum of the ijth entry of A times the ijth minor multiplied by minus 1 to the power I plus j. Okay. So, remember when I was 1, that was the definition, right. So, when I was 1, we had minus 1 to the power 1 plus j A1j M1j. Yeah. So, now what we are saying is we can replace that 1 by I, and the formula works equally well. Okay. So, the expansion along the first row was the definition that we are going to use, and what we are saying is it does not matter whether you use 1 there or any other row, you can expand along any other row. Okay. And the fact is you can even use a column to do the same thing. So, you can expand along any column. So, here notice that the j was what was varying and the I was fixed. So, this is expansion along the ith row, and this is expansion. So, now the j is fixed and the I is varying. Okay. Here I is varying and j is fixed. Okay. So, that is expansion along the jth column. Okay. So, So maybe let's do an explicit expression. Let's write down one explicit expression here. So suppose I have a 3 by 3 matrix and I want to expand along the second row. Okay. So what is this term telling me? So this is expansion along second row. So this is saying what you have to do is you have to take minus 1 to the power. So now I is 2 and now j varies. So minus 1 to the power 2 plus 1 times a21 times the 2 1th cofactor, sorry, the 2 1th minor, plus minus 1 to the power 2 plus 2 a22 times the 2 2th minor, plus minus 1 to the power 2 plus 3 a23 times the 2 3th minor. My bad, this should be 2 2. Okay, so that's the expression. So if you write it out concretely, this is minus a21 times determinant of. So you have to drop the second row and first column. So you get a12, a13, a32, a33 plus a22 times determinant of a11, a13, a31, a33 minus a23 times determinant of a11, a12, a31, a32. Okay, so I hope it's clear what we mean by expanding along the ith row. Okay, this is an example of how to do this. You can do this for an n by n matrix also. It's correct. The proof is slightly involved. I mean, it's not hard, but it involves manipulation of a lot of expressions. So if you like your algebra, I'll suggest you go ahead. And let me do maybe a similar example for expansion along the second row. Sorry, the second column. Okay, so this is expansion along second column. So what this is saying is that this is minus 1 to the power 1 plus 2 a12 times determinant of a21, a23, a31, a33 plus minus 1 to the power 2 plus 2 a22 times a similar determinant. I'll encourage you to write this down. That's minus 1 to the power 2 plus 3. Sorry, this was what? The second column. So my bad, this is a32 times the determinant of the corresponding matrix you obtain, namely, so that's the minor. Okay, so this is what we mean by expansion along any row or column, and it's a fact that the determinant can be computed in any of these ways, and it remains the same. So there is nothing special about the first row of the matrix. That's how we define it. So now that we have seen that the determinant can be computed in terms of any row or column, meaning by expanding along any row or column, we see that in particular there is nothing special about the first row, and we see that the expressions that we are getting, there is some kind of symmetry about them, but of course with some negative signs thrown in and so on. Okay, so keeping that in mind, let's now look at some properties of the determinant. So we already saw in the first video that the determinant of a product is the product of determinants, and we could do various operations on matrices, and the determinant either remain the same or change sign. So we did all of those for 2 by 2 and 3 by 3 matrices. So let's see now what happens for the general case. So I'll make these statements, but I won't really prove too many of these. Yeah, okay. So the first property that we want to look at is the product. So the same thing that holds earlier that we saw earlier still holds, namely that a determinant of a product is the product of determinants. So what we mean by that is determinant of AB is determinant of A times determinant of B. Okay, so we explicitly checked this when they were of size 2 by 2, and I said you can try to check this for 3 by 3. If you did, you must have seen that the expressions start becoming rather complicated. It's not difficult, but you have to be careful with your algebra. And so you can imagine that for 3 by 3, beyond 3 by 3, if you work it out in terms of the explicit expressions, it's going to be slightly hard. So we won't really get into the proof of this statement, but we have seen it for 2 by 2, and hopefully you have checked it for 3 by 3, so this is believable. Okay, so let's use this instead and derive some interesting formulae. So the first thing that we can do is we can ask, if you take the power of a matrix, of a square matrix, of course, namely you do a squared, a cubed, a to the power 4, a to the power n in general, then what happens to the determinant? And what this identity tells you is that you can take this power out. So determinant of a to the power n is determinant of a to the power n. Okay, the second thing that you get out of this identity is, if you take the determinant of the inverse, then that's just the reciprocal of the determinant of a. Okay, so I can write this in more fancy language as determinant of a to the power minus 1, right? So the proof of this is exactly the same as we did for the 2 by 2 and 3 by 3 case, so I'll suggest that you go back and look at it. Another very useful formula is that when you take determinant of P inverse AP, okay, so you have a matrix P, you take its inverse, so A and P are both of size, square matrices of size n by n, and P has an inverse, so you take determinant of P inverse AP, then you can use this formula and what we derived just above to get that the determinant is the same as the determinant of A. And then another thing to note, very easy fact, remember that we saw that the product of two matrices need not be even defined if you take the opposite order, and even if it is, they may be of completely different size, and even if they are of the same size, AB and BA may not be the same, but the determinant must be the same because the determinant is the product of determinants. Okay, this is, of course, remember, if A and B are of square matrices of size n by n. Okay, and the final identity that maybe one can write down, so determinant of A transpose A. So maybe before I even do this, I should ask, what is determinant of A transpose? So determinant of A transpose, so now given that we can expand along any row or column, so for A transpose, instead of expanding along the first row, we expand along the first column. Yeah, so expand along the first column. Okay, so I'll say expand along first column. So I strongly suggest you do this. Okay, and if you do that, the expressions you are going to get will allow you to conclude that this is determinant of A. So I'll leave this to you. So along with, so I should use this, so this plus what I'll call induction. Okay, namely Assume that this formula is correct for n minus 1 by n minus 1 matrices, that the transpose of a matrix has the same determinant. Then expand along the first column, and in the minors, remember, they are determinants of n minus 1 by n minus 1 matrices. So think of those as transpose of something, and you will see that you can equate these two expressions. Okay, so once we know this, determinant of A transpose is determinant of A. So determinant of A transpose A is determinant of A squared. Okay, this might not be very seem very interesting right now, but maybe at some later point you might find expressions of this type coming up. Okay, so with this long list of interesting observations, let's go on to another property. So again, we have checked this property for 2 by 2 and 3 by 3 matrices, or rather I have checked it for 2 by 2 and I hope you have for 3 by 3. So switching two rows or columns changes the sign of the determinant. So what do we mean by switching two rows or columns? Let me recall what that was. So if A is like this is the ith row, this is the jth row, so this is AI1, AI2, AIN, this is AJ1, AJ2, AJN. So we'll switch these two rows to get this new matrix A tilde. So now its ith row will be AJ1, AJ2, AJN. This is the ith row of A tilde, and the jth row will be AI1, AI2 up to AIN. This is the jth row. Okay, so we have switched these two rows, and everything else in A tilde is exactly the same as it was for A. Yeah, all the other entries are exactly the same. Okay, so then determinant of A tilde is minus determinant of A. Okay, how do we get this? So the idea is expand along the ith row and then use induction. So expand along ith row and use induction. Okay, so if you do that, you will see a minus sign coming up. Fine. Okay, let's move on to the next property that we want to discuss. I should have said in the previous slide that similarly, if you interchange columns, you get the same result. Okay. So adding multiples of a row to another row leaves the determinant unchanged. Okay, so what does this mean? So here's A, which was like in the previous slide, and what is A tilde? So let's say I add t times the jth row to the ith row. So then here I get AI1 plus t times AJ1, AI2 plus t times AJ2, and so on, AIN plus t times AJN. Okay, and the jth row remains the same, AJ1, AJ2, AJN. Okay, so the only thing that has changed is the ith row. Fine. And what happens in that case? So the claim is the determinant of A tilde is the same as the determinant of A. So again, one has to prove this. So the proof is so one way of proving this is to expand along the ith row, and then you will get two different expressions. One is just determinant of A, and the other is determinant of a matrix which has two rows which are the same, and then one will have to prove that that is 0. Okay, so that's how you can do this. Okay, so one can do this also for columns. So for columns, let's say if I want to add the kth column to the lth, t times the lth column to the kth column, then we'll get a1k plus t times a1l, a2k plus t times a2l, and so on, ank plus t times anl. This is the new kth column. Okay, and the same thing will work. Determinant of a double tilde is determinant of a. Okay, so adding multiples of a column to another column leaves the determinant unchanged. Fine. So then another property. So again, we have seen this for 2 by 2, and I left it to you to check for 3 by 3. If you multiply a particular row by a constant t, then the determinant gets multiplied by t. So the same thing holds for columns. If you multiply a column by t, then the determinant gets multiplied by t. So what is this saying? So you have a matrix A, and let's say in A tilde you multiplied the ith row by t. So you have TAI1, TAI2, and so on, TAIN. Everything else is the same. So then what you do is you expand using the ith row. Okay, so if you expand using the ith row, you get t times ai1. Okay. Before that, there's a minus sign which I should have included, meaning a sign I should have included. So determinant of a tilde, so expansion along the ith row gives us summation minus 1 to the power I plus j. J runs from 1 through n. Yeah, so maybe let me do this proof so that you get an idea of how to prove such things. So t times aij mij. Okay, but now you can take t out, and so you get minus 1 to the power I plus j aij mij. So now, so you have to be very careful here, because when you write down the minus, that's with respect to a particular matrix. So let me put this tilde here. So this is the minor, the ijth minor of the matrix A tilde. Okay, so this is the ijth minor of the matrix A tilde. But if you delete the ith row and whatever column, then the remaining matrix, remember A tilde and A have the same entries. So m tilde ij for this particular row I is the same as mij. Okay, so this is just t times summation j is 1 through n minus 1 to the power I plus j aij mij, where this is the ijth minor corresponding to the matrix A. And now this is exactly the expression for the determinant of A. Okay, so we have actually proved this. Fine. So what is the upshot? The upshot is that if you multiply a particular row by t, then in the determinant it comes out. Okay, the same thing holds for columns. So I'll suggest that you check this. So there you will have to expand along columns. Okay, so I'll also put in a warning here, because this is something that often students make mistakes with. So warning. If you multiply the entire matrix by a constant, remember that we have studied multiplying matrices by scalars. So scalar multiplication of matrices. That means you multiply each entry of that matrix by that scalar. Okay, so if you do that, and this is an n by n matrix, so just to keep track of that, this is an n by n matrix, then this is like multiplying not just one particular row or one particular column by t, but every row or every column by t. Okay, so you will pick up a t in the determinant from each row. So what you will get is t to the power n times determinant of A. Okay, where what is this n? This n is exactly the size of A, meaning the number of rows or number of columns in A. Okay, so t to the power n times determinant of A. Yeah, you won't get t times determinant of A, right? So be careful of this property. It says you multiply a row by a constant t, then that t comes out in the determinant. Yeah, if you multiply the entire matrix by t, then t to the power n comes out of the determinant. Okay, this is something students often make mistakes with, so be careful with this. Okay, so finally let me end with some computational tips. Okay, so if you have a 0 row or a 0 column in a matrix, then the determinant is 0. How do you get this? You expand along that particular row or column. Okay, the determinant of a matrix in which one row or column is a linear combination of the other rows, respectively columns, is 0. Why is that? Because you can remember, we can add multiples of a row to another row and the determinant remains unchanged. So you keep adding the correct expressions of the other rows to that particular row and you make it 0. So once you make it 0, remember the determinant remained unchanged and then you have a 0 row or column, and that's how you get that the determinant is 0. So the second property we will be using later on. So we'll come back to this if you didn't understand this. The third one is what we just saw, scalar multiplication of a row by a constant t multiplies the determinant by t. And the fourth is a general sort of tip. While computing the determinant, you can choose to compute it using whatever row or column is most convenient. Yeah, for example, as we saw in the first thing here, we used that row or column which is 0. Okay, so this is a general statement. It may be of use. Okay, so what have we done in this video? We have seen how to compute determinants. First of all, we defined determinants for square matrices, and then we saw that you can compute them using expansion along any row or column in terms of minors. And then we used that to look at some other properties. So most importantly, determinant of a product is product of determinants. Yeah, very important. So keep this in mind. And then we also saw that if you do some particular operations, namely adding two rows, meaning adding a multiple of one row to another, or multiplying a particular row by a constant, or swapping rows, we saw how the determinant behaves. So that's it for now. In the next video, we'll see how to use determinants to compute solutions to systems of linear equations.